I always forget that step for some reason. All right, guys. Well, welcome to class. Before we get started, I would just like to say a couple of things. First of all, I got everybody's midterms graded, and you'll be pleased to know everybody passed. So good job. Good job. I also graded quiz 3. Everybody passed that one as well. Great job. So the next major thing that will be due is quiz 4, and that should unlock after this class, and you guys will have all week until next Thursday to complete that quiz. All right, good stuff. So guys, I am just gonna go ahead and get started. We are covering the respiratory system tonight. And personally, I really like the respiratory system. It's a pretty cool system to get to teach. So just to start out with, we'll look at functions of the respiratory system. The primary function is always going to be providing oxygen to the body. That's like objective number 1. That's the big thing. But also, we're not just adding oxygen into the blood. The lungs will also remove carbon dioxide. So we're facilitating waste removal as well. The lungs also assist to maintain a consistent body pH, particularly in the blood. And that pH needs to be 7.4, which is just a shade on the alkaline side rather than the acidic side. The respiratory system also produces sound. So I had it posited in a very interesting way. There's a short story called Meat, and it's about aliens that encounter humans for the first time, and we are so different than any other aliens that they've encountered, and they're trying to explain how humans speak. And they're like, well, it's meat sounds. I'm like, what do you mean meat sounds? They're like, well, you know, when you like flap meat around, it makes a sound. They do the same way. They just squirt air through their meat. It's a really funny short story. There's a video on YouTube if you wanted to watch it. It's a fun little diversion, but it's called Meat. Anyway, we speak by squirting air through our meat, particularly right here in the larynx, right, where your vocal cords sit. Oops, I'm going way too far. So, provides oxygen to the body, removes carbon dioxide from the body, maintains a pH of 7.4, which is just a shade alkaline. We produce sound through the respiratory system. We also get our sense of smell through the olfactory organ in the nasal cavity. This system is used to expel excess water and heat. We also increase venous return and lymphatic drainage. Remember last week, we said just the normal breathing movement helps push lymph on through the system. And lastly, it regulates blood pressure. So blood pressure and breathing rate will be linked to each other. So now we've got an idea of what the system does. Next thing we're going to look at is the general layout. Generally, you could draw a line right about here, and we say everything above the line is the upper respiratory tract, everything below is the lower respiratory tract. So you may have heard this one particularly in relation to upper respiratory tract infections, or URTIs. We're usually talking about something like a cold, right? Like a head cold, but the cold doesn't get down into the lungs, right? You're not like, ugh. It's all up here. It's all nasal congestion and like sinus pressure, upper respiratory tract. So upper respiratory tract, we're talking about nose and the nasal cavity. We're talking about the paranasal sinuses, and we're talking about the pharynx. For the lower respiratory tract, we're talking about the larynx, the trachea, your main windpipe, and then the 2 bronchi, which will split into bronchioles and alveoli in the lungs. And as always, guys, stop me if you have any questions. Just shout out if you have questions, because I'm just a moving train. I'm gonna keep on going. All right, looking at the nose. The nose will be formed from bone. Specifically, we're looking at frontal bone, nasal bone, the maxilla, as well as a lot of cartilage. This actually doesn't go far enough. There are other bones, guys. The vomer bone forms the nasal septum. You also have the nasal conchae, which are these little curved bones that serve to get air circulating as it's pulled into the upper respiratory tract. So it cools and moistens the air. I can pull up a better picture of this on my anatomy app. I'll pull that up in just a moment. But air enters through the external nares. That's the fancy name for nostrils. Air comes in through the nostrils. Those open into the nasal cavity. And that's where your concha, the nasal concha bones come into play. You'll see there, I can't pinch and zoom on my slideshow, but they're little curved bones. So as you breathe air in, those bones kind of guide the air to start circulating. And this does a number of things. Number one, it slows the intake of air so that the air has a chance to become warmed and moistened before it enters the lungs. You guys have seen what happens when this goes wrong. You ever gone running on a cold day and you get like daggers in your lungs, like your lungs just burn with the cold air? You're breathing too quickly and the air isn't getting warmed and moistened. So it's too cold and dry in the lungs. That's why it burns. But the other cool thing is those conchae get the air circulating. So if there's any particulates, dust, random little bits of stuff in the air that you've breathed in, that circulation action throws all of those particulate bits against the walls of the compartment, and they're lined with mucous membranes. So as you breathe in dust, the air spins, dust is blown against the wall, and it gets stuck in the mucus. So we do not inhale all of that particulate matter into our lungs. So this chamber is going to be vertically divided by the nasal septum, gives you a left and a right. Nasal hair traps dust and particles. The nasal conchae, as I just said, slow the airflow, warm and moisten the air. And then your nasal epithelium, meaning just the skin inside your nose, right? All that red skin up in there, contains cilia. These are going to be little microscopic hairs, and they move together to create kind of a current so that everything gets moved in the right direction. It also contains, oops, the slightest touch sets this PowerPoint off, man. I'm telling you. There we go. Cilia and mucus producing goblet cells. Goblet cells are just their name. They produce mucus. Cool. Goblet cells trap and remove pathogens because, again, mucus. It gets stuck in the mucus. So if some foreign body gets stuck in the mucus, we just keep adding layers until eventually it starts to dry, and then, pardon my French, but now you have a booger. And there's only two directions that booger can go. We can pull it down through the pharynx, or we can eject it, hopefully into a tissue. All right, nasal cavity. We have the olfactory mucosa. This will be the superior surface. Olfactory tells you smell. It's going to have something to do with your sense of smell. The nasal mucosa has many thin-walled veins. Blood flow is increased when the air is cold. We want to increase blood flow when the air is cold so that the blood does not stay in the cold air for too long. If you slow the circulation, then the blood vessels will stay in contact with the cold air for longer. And remember, blood is trying to keep your body temperature hot. You don't want blood hanging out in places where it's really cold. You want to keep that blood circulating rather quickly. When air leaves the nasal cavity, it travels to the next part of the system, which is the pharynx. The pharynx. Now, this is one that gets a lot of people. I'm sorry, sinuses first. Well, I'll get there. I'll get there. Your paranasal sinuses. Sinuses are defined as air spaces within a bone. So we're talking about openings in a bone that are hollow. They'll be lined with epithelium, but they're open to air. This is why pressure changes create sinus pressure. So many of your bones in the face and in the cranium will have sinuses, namely the frontal bone. You've got two empty air pockets up here. You also have them in the ethmoid. The ethmoid forms the medial wall between your eye orbits. So right in between your eyes, ethmoid sinus. Behind the eyeballs, the sphenoid sinus. And then the maxilla also. The maxilla, as large as it is, it's super thin and really hollow, like very, very hollow. So all of this space here is just sinus space. So these sinuses are all going to be open to the nasal cavity, lined with epithelial tissue. They help keep the air warm and help humidify it. They also serve to lighten the skull. Bone can get a little heavy, especially when you've got a dense, thick bone. So by hollowing those bones out and filling it with air spaces, we lighten the structural, the weight of the skull. And also the exact shape and depth and size of all of your sinuses, since they're open to the nasal cavities, they will also help let sound resonate. So this is why your voice changes when you have sinus infections and things like that. The voice is using those sinus cavities to resonate those air vibrations. Okay, so here we get a lot of confusion between the pharynx and the larynx. And I know the words look so similar, it's really difficult to just tell them apart at a stretch. But here's the best trick that I have for you. It's not the best one, but if it helps, and it's free from me to you. It's my little gift. The pharynx is the upper portion of the nasal cavity. It starts at the back of the nose and it goes all the way to the back of the throat. So you are familiar with the pharynx. And again, I don't mean to be gross, but we're talking about the respiratory system. We've all hocked a loogie before. You guys know this old trick? You pull it all down from the nose into the throat. It's going through the pharynx. That's the pharynx. That's it. When you're pulling all that mucus, you're pulling through the pharynx. Then we get to the voice box. This is the larynx. This is where your vocal cords are. This is where singing happens. So the way I keep this one straight is your la 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 larynx. So the nasopharynx is the point above food entry. So the nasopharynx, this little highlighted bit here in yellow, is only the back of the nose. We draw a dotted line and stop the nasopharynx right at the back of the mouth where food enters the same tube. Now we are in the oropharynx. You get it? The oral portion of the pharynx as opposed to the nasal portion of the pharynx. You see where we're going with this? Now, once you've hocked the loogie and you've got this ball of mucus in the back of your throat, either you spit it out or you swallow it. Once you swallow, we are not in the oropharynx anymore. We have moved into the laryngopharynx. That name is telling you we are in the connecting piece between the larynx and the pharynx. Okay, so we're headed to our la 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 larynx down here. These portions here are also connected to the inner ear through those eustachian tubes. So if you ever get like an ear infection and you've got like pus draining down, you taste it in the back of your throat, that's why. It's all one tube back there. All right. Oropharynx extends from the soft palate to the epiglottis. The epiglottis is the little flap that closes off your airway when you swallow, and it closes off the esophagus when you're breathing. So normally your stomach tube is closed because you're breathing all the time. When you swallow and food is headed down the tube, the epiglottis flops over, opening up the stomach, but closing the airway. This is why humans can't breathe and swallow at the same time. Unlike snakes, however, you ever seen the inside of a snake's mouth? They've got a windpipe, almost like a tongue. Oh, if you say no, boy, let me show you something. If you have a snake phobia, trigger warning. But when you look inside the mouth of a snake, you see that little tube at the bottom of his mouth? That's the windpipe for a snake, which is why they can swallow these enormous eggs or things like way bigger than their head. They can keep breathing while they are swallowing. Humans cannot do that trick. Their windpipe and their esophagus are two separate tubes and they do not crisscross. Humans crisscross their breathing and eating tubes.
Dolphins have separate ones too.
Sorry, dolphins?
I think dolphins also have separate breathing to eating.
Yes, they would, because they have a blowhole. Yes. So aquatic mammals like dolphins and whales, if they have a blowhole, that's their breathing tube. That's where their trachea ends, is back there. which makes sense from an evolutionary standpoint, right? Because they're breaking the surface, they got to breathe and then go back down. Yes, good call on the dolphins. Yeah, but snakes are just a little more like, oh, I get it. You really see it with the snake because it's all still in their mouth, right? We didn't just evolve some blowhole on the back of our neck, which would be kind of cool, but also kind of dumb at the same time. Like, could you imagine sneezing? Someone in front of you in line sneezes and now you're covered and you're like, achoo. All right, so the oropharynx, we are in the same tube now, connecting the nose and the mouth down to the throat. So this part of the tube carries both air and food. It's lined with stratified squamous epithelium. Squamous means flat. Stratified means layers. So it's layers and layers of flat epithelial tissue. This contains your palatine and your lingual tonsils. Anyone ever had their tonsils out? No? Awesome. Good. Strong immune systems. I like it. Tonsils sit right about here, deep inside, in the mouth, but like down in here. And you never even notice tonsils until they become inflamed. And then suddenly you can't swallow and it hurts to speak and all that super fun stuff. So the laryngopharynx, now we're more here, like in the upper part of the neck. This is directly posterior to the epiglottis. It carries both food and air. And during swallowing, epiglottis will shut off access to the lungs. We don't want food in the lungs. We only want food in the stomach. But when the epiglottis malfunctions, that is what we mean when we say, ooh, my food went down the wrong pipe, right? And it gets stuck and you cough. It didn't go down the wrong pipe. Usually what happens is when the epiglottis goes to close off the lungs, the food beat it to it. So it's pinching the food against the side of the tube. And now you got to cough and cough and cough, pushing air from the lungs to dislodge that piece of food. So now the epiglottis can close and then you can swallow properly. Now when we get into the larynx, this connects the trachea through the glottis. This is made of a whole bunch of different pieces of cartilage, no bones here. The only thing that would count would be the hyoid bone, but the hyoid bone is just a fancy one. We'll talk about that one in a second. So your epiglottis, we said, this is the flap that closes off the stomach and the lungs. It usually stays closing the stomach. It only closes off the windpipe when we're actively swallowing. Once you're done swallowing, it flips back over. The thyroid cartilage is one you guys are familiar with. This is the Adam's apple. I don't have one, unfortunately, but you know, a lot of guys do. It's just cartilage. And the cricoid cartilage gives its structure and protection. Thyroid cartilage anchors your vocal cords, and the arytenoid, there we go. Arytenoid cartilage anchors the vocal cords and all of the muscles of vocalization. All right, before we get into vocal cords too deeply, I want to take a moment and just kind of catch ourselves up with the anatomy app and just get better views of what's going on. So I went ahead and pulled up the respiratory system, and I started out with the skeleton on, just so we could start to get a little bit of sense of like where things are located. Because remember, when I take the skeleton away, it's really hard to tell where we are kind of in general. So we start with the nose, right, and the mouth. We move down to the neck. There's the thyroid cartilage. So that's going to be what forms the Adam's apple. Moving down, we notice this very distinct ribbed tube. The ribbing is made of cartilage, and it's very important why this tube has this kind of reinforcement. I want you to think for a moment about your vacuum cleaner. Yeah, I know, weird stretch here. But when you got your vacuum cleaner, it's got that hose that you can use to like vacuum up high or on stairs or whatever. Think about that tube. It's thick and sturdy, and it's usually ridged because we're dealing with negative air pressure. And if the tube wasn't reinforced, the second you started to suck air through it, the tube would collapse and flatten. We can't have that when we're talking about an airway, guys. Airways have to always be open. So we reinforce these tubes with just concentric rings that go all the way down, so that no matter whether I'm breathing out or breathing in, the tube stays open. It is cartilaginously reinforced. That is an important detail. So now I'm going to take the skeleton away. And there we see the entire respiratory system. And it looks kind of like a Pokemon. So let's start up at the top. I'll turn it to the side. And again, I know it looks real weird. But you got your nose, and you can see down here the little gums and the tongue. So we know like we're in the mouth area. This little frill up top, that's the frontal sinus. That's the air pocket up here in the frontal bone. This guy right here. Here we have the nasal cavity. That's the proper nasal cavity. All these little guys are the suprabular cells. These guys are ethmoidal cells. Again, their purpose is to add resonance to the voice, and they extend along the orbital palate of the palatine bone. Here we have the sphenoid sinus. This would be found inferior and posterior to the eyes, so behind and kind of below the eyeballs. Here is your maxillary sinus. So this will sit right here in the cheek. Now I'm going to start removing things so that we can start to look inside this system. And just as I hide things and kind of pull them away, that's the nasal septum. When I take that away, there we go, beautiful. Check out those little folds we've got going on. Those, again, we're wanting to make sure that air doesn't just go straight into the lungs. It's got a good chance of getting all of its particulates filtered out. We want that air warmed and moistened as well. You can also see, guys, if we look closely, that little hole right there in that little section, that little hole, that's where the eustachian tube from the ear comes in and plugs in. So all of the stuff in the inner ear will drain down in there. That's how you get the taste of pus in the back of your throat when you have like an ear infection. That's also the same tube we use like if you get on an airplane or something and you try to equalize, plug your nose and blow and your ears pop out. It's going through that little tube. Okay, so opening this up a little bit more, here's the tongue. So right above the tongue, that's the mouth. That's the whole mouth. Your tongue is way bigger than you think it is, and it takes up a lot more space in the mouth than you probably think it does. Remember, other than when we're like talking or chewing, the mouth is closed and the tongue takes up all the space in the mouth. There's the uvula. So you see that little dangling thing in the back of your throat, the little punching bag that hangs down there. And then we can even kind of turn the image and try to look down the windpipe. Oops. There we go, beautiful. And right there, you can see the division between the white and the pink. The pink continues on to the stomach. The white is headed to the lungs. And then you have this little, where's the epiglottis? There it is, epiglottic cartilage there in green. So this little rim looking doohickey, that's the epiglottis. It normally closes off the stomach, but when you swallow, it lifts up and closes off the airway. So now we move into the lungs. So we have our trachea, that's the windpipe. That's the main one. So if you've ever heard of someone having to have a tracheotomy, where they cut a hole in the neck and put in an air tube so a person can breathe, usually from some kind of inflammatory condition, that's exactly what they are literally cutting straight through the neck into the trachea, opening up the windpipe, and you stick a tube down in there and now they can breathe. And we bypass the entire upper respiratory tract. So severe asthma conditions, severe allergic reactions, things like anaphylactic shock, where the airway closes. It's usually the airways up here that close. If we go with a tracheotomy down below, we bypass the upper respiratory system and we can get air into the lungs. The trachea will then split into a left and a right bronchus. And that's what we have shown here, the left bronchus. Now these guys will further divide into smaller sections. These are called bronchioles. And bronchioles will terminate in clusters of air sacs called alveoli. The alveoli are microscopic, so you're not going to be able to see them here. I will show you an alveoli later on. Okay, so by this point, we should have caught up with the PowerPoint. We still have a lot to cover. All right. Next thing I want to talk about are the vocal cords, which are more properly called vocal folds. They're not true cords. When we're normally just breathing, the cords are relaxed, and so they are held apart from each other. That is their relaxed position. When we talk, we engage the muscles of vocalization. The muscles put tension on the cords, which draws them together. So then what happens is, like I was saying, you squirt air through your meat. We pull the cords apart just enough to allow air to squeak through, and then that movement of air causes a vibration in those cords against each other. That vibration is what creates your voice. All the sounds that you can make, all the sound effects you can do, all the fun character voices, it's all modulating the tension and the length of the vocal cords, as well as affecting the resonance of the sound in all of your vocals and all of your sinuses. So these elastic ligaments are strung between the arytenoid and thyroid cartilage. Air passing over the cords, more accurately, is between the cords, right? Between the two cords. Vocal muscles will change the cord length and the cord tension. This changes the pitch of your voice. So when you relax them a little more and give them a little more slack, the bass of your voice comes out and suddenly the voice drops really low. But when you stretch the cords and put a lot of tension on them, the voice goes up really high. Other things that affect the vocal cords, testosterone. You ever been around a teenager who went through puberty and suddenly that 9-year-old kid who's got his little high, squeaky little boy voice, and suddenly you see him the next weekend, hi, I'm 13 now. Testosterone will definitely affect the tone of the vocal cords. Also, conditions like laryngitis, the inflammation affects the movement of the vocal cords. That's why you lose your voice. If they can't be pulled together and there's too much space between them, then you get this really breathy voice. Another cool thing that goes on in the larynx is the cough and sneeze reflex. The main division, just to keep them straight, sneezing is an upper respiratory tract thing. Coughing is a lower respiratory tract thing. So coughs and sneezes are triggered by sensory nerves that are detecting irritants. Deep inspiration is the technical word for breathing in. You can also use the word inhalation. They mean the same thing. Deep inhalation is followed by a contraction of the expiratory muscles with the glottis closed. The expiratory muscles are the muscles that help you breathe out. So we close off the glottis so that the stomach is closed, and we breathe in, close off the stomach, and squeeze all the muscles that breathe out. That's a cough. As pressure builds up, the glottis opens and the air leaves explosively. So if there's something in there, hopefully we expel it. That's the purpose of a cough, is to get it out of the lungs. In a cough, air is directed through the mouth. In a sneeze, it's directed through the nose and the mouth. The illustration here on the slide is the sneeze reflex arc. It's fascinating information, but we haven't talked about reflex arcs, and we won't talk about those until we get to the nervous system in Anatomy 3. So cool little thing, probably not for us to worry too much about. Okay, trachea extends below the cricoid cartilage about 4 inches before branching into the bronchi. So your trachea is only about 4 inches long, and it says right about there. Right about there. So right about the mid part of your chest is where your bronchi split off and go towards each lung. There is a series of C-shaped cartilages that keep it from collapsing while also providing flexibility. So the tube can bend around, but it doesn't collapse when we breathe in. The C opens towards the esophagus, allowing the expansion of the esophagus during swallowing. And if the upper respiratory tract is blocked, the medical procedure is a tracheostomy. We cut a hole in the trachea. Tracheostomies are I don't. Okay, sorry, my brain got stuck. I didn't think it was the right word. I got stuck between tracheotomy, which is the one I learned. It's the ending otomy always means you're cutting into something. But an ostomy, usually with ostomy, you're thinking about some kind of bag, like a colostomy bag, right? But thank you, Google. You straightened me out. The words are interchangeable. Welcome to anatomy. Tracheotomy or a tracheostomy is a surgical procedure which consists of making an incision on the anterior aspect of the neck and a direct opening airway through that incision into the trachea. And we won't usually see the incision. That's handled by, medical people do all that stuff. But that's usually what you see. Ooh, here's a cool picture. Yeah, you can see the cartilage ribs on the trachea. Okay, trigger warning's over. Okay, now we're getting into the bronchi. So the bronchi are the main tubes, the branches that lead into the lungs. You have a left and a right. The walls of smaller branches contain less cartilage and more smooth muscle, which will allow them to expand or contract based on needed air volume. Muscle walls relax under sympathetic stimulation and the airway opens, because when we are stressed, we need lots of oxygen to the muscles. Muscle walls constrict under parasympathetic circulation, airway closes, because when you're resting and digesting, you don't need a whole lot of air. Muscle walls also constrict under the influence of various chemicals like histamines, right? So when you have allergies and your airways closed, and then we take an antihistamine and it opens those airways again. Yep. What else? Primary left and right bronchi are the two main branches that enter the lungs. They branch into secondary bronchi. Those would be all the mid points. And then you have tertiary bronchi, which are the small little stems at the ends. Each of your secondary bronchi will serve one lobe of a lung, and lungs have a set amounts of lobes. You have 2 lobes in your left lung, 3 lobes in the right lung. I'm going to flip back to our anatomy app. Show hidden. And you can actually see them. On the right side, you have 1, 2, 3 lobes. The left lung, you only have 1 and 2. And there is a reason for this. The reason is a lot of the space where the left lung would have an extra lobe is taken up by the heart. So you only get 2 lobes in the left lung. The right lung gives you 3 lobes. So when we're looking at not the primary bronchi, because you only get 2, a left and a right, the secondary bronchi head to a lobe. So you have 3 secondary bronchi on the right side 2 secondary bronchi on the left side. Good stuff? Good stuff. The tertiary bronchi are the tiniest ones. They will branch into smaller and smaller bronchi until they finally end in bronchioles, which are tiny little ones. And then the bronchioles terminate in alveoli. Alveoli is the plural form, singular alveolus. These guys are under 1 millimeter in diameter. They are microscopic. They are a single cell thick using squamous epithelial tissue. So just a thin, flat little cell kind of curved around into a ball shape. And I have a really, really good model of alveoli on my anatomy app. So these contain more smooth muscle than the other branches because these are the ones doing the thing. These are the guys that are holding the air and exchanging it with the blood. This is where the magic happens. So we need a lot more smooth muscle to expand or contract these alveoli based on how much lung volume we need to use. Respiratory bronchioles lead to alveolar ducts. Alveolar ducts lead to these grape-like clusters of alveoli. Oops, no, that's what I meant. So, from the trachea to the primary bronchus to the secondary bronchus. On the left lung, we have one heading to the superior lobe, one going to the inferior lobe. Then we have our tertiary bronchi. These guys will terminate in what is known as a bronchial tree. It's coming, sorry. My iPad is old and slow. Here we go. So here is the terminal bronchiole. So this is the last bit of windpipe that we have. We are getting into the microscopic range now. A cluster of air sacs looks like this. This is an alveolar cluster. Notice the replete blood vessels. They are coated in blood vessels. You'll also notice arteries and veins, right? But remember, these guys are coming from the heart and going to the heart. So arteries are blue and veins are red in the lungs. This is the only time we get to mix match our colors here, guys. So when we cut into them, we see, first of all, very, very thin walls. These walls are a single cell thick, and those cells are flattened like pancakes. There is very little in terms of membrane between the oxygen and the blood. We don't want a whole lot of layers between them because the lungs are relying on diffusion. Diffusion is a passive process. The other thing you'll notice is each of these chambers has little holes. So these chambers are all interconnected. We don't fill one and then fill the next and then fill the next. They all inflate together and they all deflate together. Good stuff? Cool. Now, let me lay a little more knowledge on you guys. Since we are relying on diffusion to get gas across the membrane, you have one side of the alveoli that is filled with air. The other side of the alveoli is covered in blood vessels. The name of the game is surface area. We need a lot of surface area, but space is at a premium. I only have so much space inside my rib cage. So the way we get around needing all of this space, but not having a whole lot of real estate available is we do lots of folds, lots of folding. This is why if you were to take the surface area of the lungs and open it out flat, I mean, peel open each little grape, lay it out flat, iron them down so that you have all of the exchange surface of the lungs available, laid out flat, your lungs have the surface area of a tennis court. A tennis court, all bundled up inside your lungs. Surface area is the name of the game. We need a lot of surface area to provide the location that we need for this gas exchange to occur. Now, This is where smoking comes in. You guys are familiar with the condition called COPD, chronic obstructive pulmonary disorder? COPD is a secondary condition that arises from cigarette smoking. And what happens with COPD is all of these little walls start to break down. They become damaged, they get replaced with scar tissue. But what happens is, instead of having lots of little clusters, you have a few large clusters, and we lose surface area. And when you lose surface area in the lungs, gas exchange cannot occur at its optimal rate, meaning as you breathe, you can't get enough air. You're breathing, but the lungs can't process oxygen the way that they were able to when the alveoli were healthy. So with COPD, these interalveolar walls start to break down. And so instead of having, a nice cluster of little air sacs, you have a bundle of just a few air sacs, and it is not efficient enough. It is not efficient enough. Usually in the advanced stages of COPD, they have to put the little cannula on them, the little nose tube, and give them straight oxygen. Because if you can't process bulk amounts of air, right? I can only process smaller amounts of air, then that air needs to be oxygen enriched. I need way more oxygen in that small amount of space. Make sense? Yeah. Lots of blood vessels. Lots and lots of blood vessels. All right, so there are your alveoli.
Yellow, the yellow supposed to be, is that just more blood vessels, but they didn't want to make it
Nope.
complicated looking?
These are elastic fibers. Elastic fibers. And I'll throw because I get a lot of students that mix these up. Elastic and like the quality of elasticity. Elasticity does not mean it will stretch. That is extensibility. Elasticity means once it has been stretched, it snaps back to its original shape. That is elasticity. You ever played with silly putty before, right? You stretch out silly putty and you let it go and it just drops to the floor. It's extensible. It's not elastic. A rubber band is elastic because once you stretch it, it snaps back to its original size. That is what these fibers are meant to do. After a deep inhale, and all these air sacs have been stretched, once you exhale, they snap back to their original size because of the elastic fibers. Good question. Thank you for asking. Oh, and you can see inside the airway too. Look at that. Ooh, magic school bus time. Ooh, must be so much fun to be air and have no idea which tube you need to go down. Okay, that was fun. All right, everybody clear on what we've been talking about so far? Bronchioles, bronchi, alveoli, upper respiratory tract, all that's cool, cool, cool. Okay, as I said, alveoli are the site of gas exchange. This is where the magic happens. These guys are the whole point of the entire respiratory system. It comes down to these guys. They are lined with simple squamous epithelium. Simple means one layer. Squamous means flat. So one flat layer of pancake-like cells. That is what forms the entire walls of these alveoli. Their outside surface are covered in capillaries, which is what we saw. Air passes through a thin layer of the alveolar wall. Those are the inner chambers with all the holes inside that we saw. Air passes through all of those. They also contain macrophages for defense, because remember, anytime outside comes inside the body, it is contaminated and it's got to be monitored by the immune system. That's what your tonsils are doing. They're inspecting all the food that you take in for bacteria and parasites and whatnot. You do the same thing in the nose. We do the same thing, guys. Anytime the body opens up to the outside world, you know what I'm talking about? All of those areas too. All those areas too. The lungs also contain a surfactant, which helps reduce surface tension. which prevents the lungs from collapsing. Remember, when you get down to the microscopic level, surface tension becomes a big thing. You ever seen a bug sitting, like standing on the surface of water, right? And it doesn't weigh enough to sink through, but it weighs enough that it creates like a depression on the surface of the water. Yes. When you get down to the microscopic stuff, something like surface tension is a big deal. On our level, surface tension is nothing. But in the lungs, whew, big deal. Okay, so the lung overall, composed of bronchi, bronchioles, alveoli, we have blood vessels, nerves, and a ton of membranes. They are located on either side of the mediastinum. This is just the mediastinum is let me pull up a definition for you. It's the division in the chest between left and right. A membranous partition between two body cavities or parts of an organ, especially that between the lungs. So there's a fascia drape between the left and right lungs. That is the mediastinum. Apex projects above the first rib. So the top point of the lungs stick out just above the first rib. Here is my clavicle. Your first rib is superior to that. So the lungs go pretty high up. The hilum is the site where the bronchi, nerves, and blood vessels enter and leave the lungs. Let's see if I have my hilum. I've actually never heard that word before, hilum. I'm looking for it. Nope, the only one this app will show me is the hilum of the ovary, and that is not on our agenda for today. There's another structure. The lungs do not just exist in the chest. As with most of your organs, they're wrapped in a layer of fascia. In the case of the lungs, it's called the pleura. The pleura. You guys have ever heard of the disease called pleurisy? Pleurisy? Pleurisy, a condition in which the pleura, two large, thin layers of tissue that separate the lungs from the chest wall, become inflamed. Also called pleuritis. It just causes pain, and chest pain and breathing pain. Okay, and last tidbit, each lung is divided into lobes. The right lung has 3 lobes. The left lung has 2 lobes because the left lung has a lot of space taken up by the heart. There we go, pleural membranes. These are 2-layered serous membranes, very similar to the pericardium, very similar. The visceral layer, visceral means organ. So the visceral layer, the organ layer, is the layer that is in contact with the lungs. The parietal layer, the word parietal means wall. Like the parietal bones, they form the wall of the cranium. The parietal layer, the wall layer, is the one that is in contact with the thoracic wall. Names make sense? Pretty straightforward stuff. I love anatomy. There is space between these 2 layers, between the visceral and the parietal layers. It's filled with fluid because we cannot have any friction happening. 0 friction in the body can happen. And anytime 2 things move against each other, it's going to create friction unless we add lubrication to it. That's what this guy does. Pleurisy is a condition caused by inflammation of the pleura. That's also where the lung cavity gets its name from. It's called the pleural cavity, from the pleura. Or if it's easy, because there's two lungs, so they're plural. Bad joke, I know, bad joke. Okay, pulmonary circulation. Wow, I think this is a good place to take a pause, and let's take a quick break before we jump into this, because we're skipping topics here. Okay, before we take a break, everybody good on what we've covered so far? I know we've covered a lot, but everybody's feeling confident so far? Right on, right on. Let's take a 10-minute break. Nope, sorry, wrong button. Let's take a 10-minute break. I'll see you guys back at 2 after. All right, we are back. So we left off just about to talk about pulmonary circulation. So circulation from the heart to the lungs and back to the heart. This should be a story that we are familiar with. So there shouldn't be a lot of new material here that we haven't covered already. So we start with deoxygenated blood entering the right atrium of the heart from the rest of the body, and then it goes down into the right ventricle. Right ventricle pumps blood into the pulmonary trunk, and the right and left pulmonary arteries enter the lungs, feeding into the arterioles. So we're bringing blue blood into the capillaries surrounding all of those alveoli. The arterioles lead to capillaries surrounding alveoli. Gas is exchanged. So the blue blood turns red, right? Carbon dioxide diffuses out of the blood into the lungs, while oxygen diffuses out of the lungs and into the blood. The blood keeps on circulating. So the oxygenated blood, now the red blood, goes into venules and then pulmonary veins. It's the only time we have red veins, guys. Pulmonary veins leave the lungs. They enter the left atrium and then down into the left ventricle. The left ventricle pumps the oxygenated blood to the aorta, and then from there it goes on to the rest of the body. We remember that story, right? Old news at this point, nothing new. Nothing new here. Cool. So there's a fun little diagram. Same stuff, just blood circulation to the lungs, back to the heart. We already know this story, so forgive me for skipping past it. Okay, there are multiple types of respiration. Generally, I say 3 types of respiration. Maybe there's another one coming up. External and internal respiration has to deal with the movement of those gases. External respiration is what you normally call breathing. That is exchanging gases with the external world, the outside world. So movement of air and exchange of gases in the lungs. Oxygen moves from the air into the blood. Carbon dioxide moves from the blood into the air. Primary or external respiration. Internal respiration is what happens with the blood next, right? Now that the blood is red, it goes to the heart and then gets pumped out through the rest of the body. Once we get down into the level of a capillary, anywhere else in the body, this could be in a muscle, this could be in the skin, this could be in an organ, this could be in the brain, this could be literally anywhere. When we get down to the level of a capillary, internal respiration is where the oxygen diffuses out of the blood and into the tissues. Meanwhile, the waste products in the tissues diffuse into the blood. Internal respiration is where the red blood turns blue. And now we resume our journey back to the heart. Good stuff. Internal respiration is the respiration between the blood and cells. The third kind is cellular respiration. Cellular respiration occurs within the mitochondria. So what's the one thing we know about mitochondria, guys? Go ahead and say it. Go ahead and say it. Yeah, Lindsay, you're muted, but I could read your lips. You got it right. Mitochondria is the powerhouse of the cell because they produce ATP. How? They produce ATP by oxidization, or I think I didn't say that word right. Oxidation, that's what happened, oxidation. So cells need oxygen because they burn it for energy. Energy in the form of ATP. That's what mitochondria do. That's why they're important. That's why we keep them around. That's why they're doing what they're doing. Cellular respiration happens inside of a cell, particularly in the mitochondria. Cellular respiration involves chemical reactions using oxygen, and the byproduct is carbon dioxide. So now it all comes full circle. Let me think. I'm just trying to think. There's a whole lot of stuff going on in a mitochondria. It's outside of our scope as massage therapists to really talk about how mitochondria do what they do. I think it's sufficient for us to understand the name of that process is called the Krebs cycle. Does that sound familiar? Like high school biology flashback? the Krebs cycle or the citric acid cycle. It's like a 16-step chemical process. It is not in our purview to understand how the process works. It's called the Krebs cycle. It happens in the mitochondria. We burn oxygen, we produce carbon dioxide, and bibbidi bobbidi boo, we have turned oxygen into waste product. Now, the end result of the Krebs cycle, and I will take a second to explain this one because it's cool. So when we go through the Krebs cycle, and again, the Krebs cycle is a very complicated chemical reaction. I'm just going to pull up a little diagram here. The Krebs cycle looks like this. And in high school biology, we go through the entire thing and we understand every phase of this process. As a massage therapist, another medical specialist, that's not us. But you see what it is, we understand, okay, cool, Dave, it's really complicated. Glad we don't have to learn it. But here's what I do want you to know. The point of the Krebs cycle, where am I going here? The whole point of the Krebs cycle, when it's done, what are we left with? 4 things. Carbon dioxide, water, a little bit of ATP, and excess energy that is in the form of heat. So when the cell goes through its Krebs cycle, this is what results. We have taken in nutrients and oxygen, we have combusted them for energy, and now the cycle ends with the production of ATP. ATP was the whole freaking point. The whole reason of doing the Krebs cycle is to get ATP. That is the energy currency of a cell. Anything a cell's got to do is going to cost you in terms of ATP, right? Think about your life. You can't even turn on a water faucet. You're going to get a bill for that water, right? Everything you do in life, all the water you drink, all the food you buy, it costs money. Same thing with a cell. Ain't nothing in this life free. So we run through a round of the Krebs cycle. We end up with a little bit of ATP. That's the whole point, is to obtain energy. We also end up with excess CO2. CO2 is a waste product. It is toxic to our body. So it diffuses into the bloodstream. It will get carried to the lungs, and then we exhale it and we get it out of the body. We also end up with a little bit of H2O. That's water. And your body does not get rid of water. That's going to be recycled. That's going to be reused. That can be reabsorbed through osmotic pressure into the blood, and it will rejoin blood plasma. It could also hang out in the tissues as interstitial fluid until it gets taken into a lymphatic vessel, and then we call it lymph. But water is not a waste product. Your body will recycle that. The last thing we produce is heat, and that is how we are able to maintain an internal body temperature of 98.6 degrees Fahrenheit. That's where the body heat comes from, is these little chemical explosions happening in the mitochondria in every cell of every part of your body all the time, forever. So think about something like this. The production of heat will be linked to the rate at which your cells are undergoing the Krebs cycle. Meaning, one more thing. And when we talk about the rate at which your cells go through the Krebs cycle, we're talking about metabolism, right? The normal rate that your cells digest, burn, reproduce, eat some more, the whole cycle that they go through, that's your metabolic rate. So when metabolism goes up, when the rate of the Krebs cycle goes up, we produce more heat and ATP and carbon dioxide and H2O. But going through more Krebs cycle just gives us more ATP, but it also produces more heat. This is how your body, or why your body heats up through muscular activity. Because when you're consuming a lot of energy, we have to produce a lot of energy, and you can't make ATP without heat as a byproduct. So when you exercise, your body temperature increases. This is also why when we're sick, right, your metabolism is kicking into high gear, fighting this infection. So as we increase our ATP, we also increase our heat, but we're not increasing our caloric intake because when you're sick, you're not hungry. So you're burning all this energy, but you're not taking in nutrients. That's why you lose those extra 5 pounds when you get a bad cold. You guys know what I'm talking about, right? That nice little bit of weight loss you get after a nice bout with the flu. Trust me, I love it. I lose about 5 pounds after the flu. I hate being sick, but ooh, I love that post-flu waistline. All right, cellular respiration, the third kind of respiration. One more time. External respiration happens in the lungs. That's normal breathing, exchanging gases with the outside world. Internal respiration happens between the blood and the cells. That's what's going on in the capillaries, letting oxygen out into the tissues. Cellular respiration happens in the cell. That is how ATP is produced. Particularly, it happens in the mitochondria. I'm not sure if I don't think we're going to go into this today, but I will just add a little something. Cellular respiration comes in two main kinds. You have aerobic versus anaerobic respiration. Aerobic happens in the presence of oxygen. This is the one you're all using right now. Nice, calm breathing, happily. No test today, no homework tonight, just nice and relaxed. But when I tell you, guys, there is a 100 question, very hard test that happens after this class today. It's very hard. Suddenly my heart rate goes up. Oh God, I didn't even study for the test. It wasn't on the syllabus. I didn't know about a test. And now we start to panic. And as we start to panic, we move into anaerobic respiration in the lack of oxygen. Anaerobic respiration is what's happening during something like a really intense workout. Okay, so as you're walking casually into the gym, we're in aerobic mode. When we start working out, your blood pressure goes up, your body temperature goes up, and you know the part in the workout where like, I can't have a conversation. I can't breathe enough to talk to someone. Leave me alone in the gym. Let me focus on my thing. If you can't carry on a conversation because you're working out so hard, you're in anaerobic mode. What else would I say? Oh, this is the point. This is what I wanted to show you. Aerobic respiration is by far the more efficient. In the end of a Krebs cycle, you produce a set amount of ATP. For aerobic respiration, you produce about 32 moles of ATP. A mole is a unit of measurement in chemistry. Doesn't matter to us what it is. It's a unit of measurement. You get 32 of them. 32 moles of ATP per round of the Krebs cycle when we are in aerobic respiration mode, normal mode. However, when we move into anaerobic respiration, this one is far less efficient. Suddenly we are burning lots of energy and we don't have oxygen available to replenish that energy. So when we go into anaerobic respiration, we have to start burning other chemicals, name things like fat, for energy. When you go through anaerobic respiration, we only produce 2 moles versus 32 moles. That is why we cannot exercise forever, because eventually you will run into an oxygen debt. You are consuming more energy than you can create. That's why you can't work out forever. And at a certain point, you will run out of ATP. There is no more. The bank is empty. Your credit cards are maxed. Your credit score is too bad for a loan. When you are out of ATP, that is muscle fatigue. You ever seen the bodybuilders who overdid it and they're like belly crawling to their car because like they can't stand up anymore? Their legs are all wobbly and they won't work. That's what happened. They burned all of their reserves of ATP. Now the body is only able to produce 2 moles of ATP per round, and it takes a while to build those reserves up again. So when you overdo it at the gym and your legs go all wobbly and you can't stand up anymore, it takes a while, But once your reserves are replenished, your muscles will function normally again. But that's what muscle fatigue is all about. It's the incurring of an oxygen debt, because working out burns energy faster than we can make it. Cool. So the next thing we're going to talk about are various factors that affect pulmonary ventilation, breathing. What helps, what hurts, breathing. When we're dealing with the lungs, the entire name of the game, I know I said the name of the game was surface area, but that's for gas exchange, right? To move gases across the membrane, it's all about surface area. For just normal breathing, it's all about air pressure and how air pressure is going to work. Changes in the volume of the lung create pressure changes. So as the lungs squeeze in, the pressure goes up. We increase the pressure when we contain the space. When we expand the space, we lower the pressure. All of these constant volume changes and pressure changes lead to the flow of gas trying to equalize the pressure. So when we take in a lung full of air, we expand the lungs and we pack it full of oxygen. This creates positive pressure. When we exhale, we open the throat nice and wide, we contract the muscles, we sink the ribs down, we squeeze the lungs. Squeezing the lungs shoots the air pressure up. We've created a very high pressure environment. Nature does not like this. Nature does not like a gradient where there's high pressure over here and low pressure over here. Nature wants to equalize all of this out. So when we squeeze the lungs, the way we equalize that pressure is by forcing air out of the system. The less air there is, the pressure drops and becomes equal inside the lung from outside the lung. So if I could explain this another way, do you guys know what a bellows is? You've seen them in cartoons. They're these paddle things. You put them in the fireplace and like, you know what I'm talking about? Yeah, okay, a bellows. So when you open the bellows, you're creating negative pressure inside the bellows. And the way nature equalizes it is by pulling air into the bellows. You open it up, air is pulled in. Then you squeeze it. The pressure shoots up. And to equalize the pressure, air is forced out of the bellows. Follow me? Your lungs work exactly the same way. That's literally exactly how they work. By opening the bellows, we pull air in. By squeezing the bellows, we force air out. That's how breathing works. So when we talk about how do you open the bellows, Dave? How do you open the lungs? The diaphragm, internal and external intercostal muscles. Also, other accessory breathing muscles like scalenes and a little bit of SCM, those little neck muscles, particularly in things like forced inhalation, will lift up on the ribs, giving the lungs a little more space to expand. So we get those bellows open real wide. When we breathe in, the diaphragm drops, the ribs raise up. So think about grabbing the top handle and the bottom handle of the bellows. Ribs go up, diaphragm goes down. You open the bellows. Inhalation is the active phase of breathing. That is the one that requires muscle contraction. You have to put effort to breathe in. Breathing out is the relaxation phase. When the diaphragm relaxes, it raises up to its normal position. When we relax these muscles, the ribs drop down. So when everything relaxes, the diaphragm goes up, the ribs go down. We squeeze the lungs. Just like squeezing a bellows that forces air out of the lungs. This whole thing deals with negative pressure. Cool. So if you understood the story that I just told you, that's exactly what this slide is telling you, just in much more boring, much drier terms. All right. Other factors involved, lung compliance. Lung compliance deals or refers to how easily the lungs will expand during inhalation. So you want lungs to be nice and stretchy. So when you push air in, they expand really easily. You don't want the lungs to resist inhalation. You don't want them to fight to have to open up. You got to get air in a lot. So we want high lung compliance. Lower compliance increases the work of breathing. I have to work harder. I have to use more forceful muscle contractions to open the bellows and pull air in. Compliance will decrease with things like lack of a surfactant. So your lung chemistry is off. You're not producing enough mucus. Scar tissue, which is things like COPD that we talked about earlier, as scar tissue reduces the available surface area. Remember, we said it was caused by scar tissue. Lung tissue is nice and stretchy. Scar tissue is not stretchy. So if you damage the lungs are repaired, but we repair them with scar tissue. Your lungs are not as stretchy anymore. Low lung compliance. Also, fluid in the lungs. I know this may come as a big surprise to you guys, but lungs were designed to process gas, not fluid. So water in the lungs, that is why drowning is such a detrimental thing. If there is fluid in the lungs instead of gas, the lungs don't expand like they're supposed to. They are meant to deal with air. So any kind of fluid in the lungs, whether that's water, you're drowning. Whether that's vomit, right? Like aspirating, you threw up and it went into the lungs. You could be talking about something like pneumonia. So the fluid in the lungs could be blood, it could be pus from an infection, anything. Any kind of fluid in the lungs is bad news. We also look at lung elasticity. So real quick, compliance talked about how easily they expand, how easily they stretch. Elasticity is not about stretching, it's about snapping back. So lung compliance deals with the lung stretching. Lung elasticity talks about it snapping back to its original size after exhalation. Cool. Lung elasticity refers to how easily the lungs recoil during expiration or exhalation, same thing. Lung elasticity decreases in emphysema. Used air remains in the lungs after expiration. You don't want old stagnant air staying in the lungs for too long because that gas is rich in carbon dioxide, not oxygen. So as you keep breathing, your cells aren't exchanging oxygen for carbon dioxide. They're not exchanging anything. If there's carbon dioxide on both sides of the membrane, diffusion doesn't happen. Remember, diffusion is all about the gradient. You got to have a lot of something on one side, not a lot of the same thing on the other. If you've got the same thing on both sides, it's equal. Diffusion doesn't occur. So your blood does not turn red. It doesn't get oxygenated. And now your whole body feels really tired because you're not getting air. Another thing that could affect pulmonary ventilation, resistance to the airflow. We're usually talking about something like your airways are constricting. So if the tubes shrink down, muscles could be working fine, lungs could be working fine, but if you can't get air into the lungs, perfect lungs don't do you any good. Ask anyone with asthma, right? So the resistance to the flow of air is usually due to friction. Breathing becomes more difficult if you increase the resistance in the airway. Resistance is controlled by autonomic nervous system. Remember, autonomic means automatic. It's just the part of the brain that deals with all the automatic stuff. Hormones and chemicals also can affect this. So for a few examples, I go back to antihistamines opening the airways. You also think about like your asthma inhalers. Those chemicals also open the airways. Vicks Vapor Rub, that'll do it. Anyone raised in a Hispanic household, mama put Vicks on your chest, and that was like the cure for everything, right? Cold, flu, diarrhea, headache, whatever's wrong with you, Vicks on the chest. That opens up your airways. Other chemicals that'll do the same thing, capsaicin, peppers. Peppers will do the same thing. So other things that will do it, the presence of mucus. So excess production of mucus will do that, as well as fluid swelling, edema. Those will also increase the resistance to getting air into the lungs, making breathing more difficult. Good stuff. All right, muscles of respiration. Ah, crap, I may have gotten ahead of myself earlier. Muscles of respiration. First is the diaphragm. The diaphragm is unique. It is a dome-shaped muscle, or umbrella-shaped, if you will. It's controlled by the phrenic nerve. When it contracts, it flattens. So very much like an umbrella, guys. Think about an open umbrella. You grab the little doohickey, you pull down, and the umbrella collapses. That's just like the diaphragm contracting. When it contracts, it moves downwards and it flattens out. This drops the floor out from underneath the lungs, giving them room to expand. That muscle is responsible for 75% of your air movement. Most of your normal relaxed breathing, the diaphragm handles it all by itself. It's quite capable. However, in terms of things like forced inhalation or forced exhalation, and just to give you some examples of what I mean, ever been held underwater for just a little bit too long? And when you finally break through, you take that nice deep breath of air in. That is forced inhalation. Forced exhalation, blow out a birthday candle. That's forced exhalation. Not normal, right? The breathing that happens and you don't even realize you're breathing, that's the diaphragm. When you suddenly need to really focus to take a breath in or push a breath out, you're usually having to recruit your accessory breathing muscles now, like the intercostals. The external intercostals are the rib lifters. They lift up on the rib cage, assisting with inhalation. When you lift the ceiling off the ribs, that are off the lungs, that gives them more room to inflate. So the external intercostals lift the ceiling, the diaphragm drops the floor. And now we have a lot more space for the lungs to expand. External intercostals account for the remaining 25% of the airflow. So the diaphragm is the name of the game here. The internal intercostals, on the other hand, are the rib puller downers. So when you blow out a birthday candle, the diaphragm relaxes, going back up to its normal position. The internal intercostals pull down on the ribs. So we raise the floor, we drop the ceiling, and we squeeze the lungs, pushing air out. Other accessory muscles include the SCM, particularly the sternal attachment. It grabs onto the sternum and lifts up. We also have scalenes, like anterior and middle scalenes here on the side of the neck. We have serratus anterior and pec minor. Pec minor is also a rib elevator. It assists with rib elevation during forced inhalation. Yeah, and there's internal intercostals. Pull down on the ribs during forced expiration. All right, abdominal muscles. Abdominal muscles don't really do a lot directly to help breathing, but when you contract your abdominal muscles, it compresses the abdomen, which pushes up on the diaphragm, squeezing the lungs. So you end up with abdominal muscles like transverse abdominis in particular, aiding with respiration by compressing the abdominal contents. Squeeze the belly, push up on the lungs. All right, so several terms that we would talk about. Respiratory rate. I will give you 5 guesses what we think we mean by respiratory rate. It is the number of breaths per minute. Usually we take about 20 breaths a minute. 20 breaths per minute is a fairly average number. We also understand though, that when we start exercising or we get into a fight with someone or we get super stressed out, respiration rate goes up. That is a byproduct of the activation of the sympathetic nervous system. So after the fight, right? We're back home on my couch in my socks, hanging out. Parasympathetic system is now engaged. parasympathetic system lowers the breathing rate and brings it back down to our normal. Tidal volume is the amount of air that moves in and out of the lungs with each breath. The lungs do not completely empty with every exhale. Some of the gas will remain. The tidal volume is how much of the gas does not remain. It gets pushed out and refreshed with the inhale. The total lung capacity is exactly what it sounds like. The total amount of air that your lungs can hold fully inflated. So when we talk about things like respiratory disorders like COPD or emphysema, the total lung capacity is lowered. When they fully inhale, they are not getting as much oxygen as a healthy individual. Inspiratory capacity, maximum volume of air that can be inspired after normal respiration. Pretty clear, yeah? Total amount of air that you breathe in with each inhale. This does not count the air that stays in the lungs from breath to breath. That is the expiratory reserve volume, the volume of air that can be forcefully expired after normal expiration. So your expiratory reserve volume, I'll show you a trick. Casual, normal breath in. Ready? 1, 2, 3. Normal breath out. At the end of a normal breath, pause. Now, push out all the extra air. There's a lot more air in the lungs after we exhaled. That is the expiratory reserve volume. Good stuff, fun stuff. All right, residual volume. That's the air remaining in the lungs after a forceful respiration. You want to remain, or you want to keep some residual volume because you got to keep some air in the lungs. Remember, the inner wall of the lungs are coated in mucus, so they're sticky. So if you fully exhale, and I mean suck all the air out of the lungs, once those sticky mucus covered walls touch each other, they stick together. And now you have to force air into the lungs to separate those. This is what we talk about when we talk about a collapsed lung. The sticky sides of the lung have touched each other and the lung kind of collapses and it won't reinflate. You have to be quite forceful, forcing air into the lungs. Good stuff. So residual volume, the amount that just stays forever, always, even after a forced exhalation. Vital capacity. Vital capacity refers to the volume that can be breathed out after maximal inspiration. The maximum amount of air available during exercise and things like that. And then the anatomical dead space is the volume of air that's in the respiratory passageways, but that air is not available for gas exchange. What we mean is, take an average breath in and hold it. So when you hold it, there's air in your lungs and gas exchange is occurring, but there's also air in the bronchioles and in the trachea. Gas exchange is not occurring here. That is the anatomical dead space. It's full of air, but we're not exchanging gases. Good stuff. Pretty self-explanatory for the most part. To keep these straight, I would recommend flashcards. All right, gas exchange in the alveoli. I believe I had talked about this already. Sometimes I get ahead of myself. I really like teaching, so I just explain everything. And then I realize I explained everything that was coming like 5 slides from now. Welcome to my life. I do believe that we have touched on all the major things on this slide so far. Gas exchange occurs through diffusion, through the respiratory membrane. This occurs in the alveolus. Oxygen moves into blood, carbon dioxide moves into the air. We've talked about this. The thickness of the respiratory membrane increases, the exchange rate will slow. The membranes have to be thin. If the membranes are thicker, diffusion happens more slowly. We cannot sit here and wait and wait and wait for the lungs to turn gas over to the blood. This has to be a pretty quick process. So we need that layer to be really thin. If the surface area of exchange decreases, the exchange rate slows. That's a lung disease. That's exactly what we're talking about with COPD. The name of the game with the lungs for gas exchange is surface area. If you reduce the surface area, you do not get gas exchange occurring. That is some kind of lung disease. Now, which lung disease you have will be determined by where the problem is coming from, what kind of problem is it, fluid in the lungs, is it edema, is it scar tissue, is it smoke damage from like being in a house fire, right? The cause is still up for debate, but the result is we've lost surface area, so lungs don't lung properly. All right. Oxygen transport in the bloodstream. Oxygen isn't very soluble in water, so only a very small amount of oxygen is dissolved in the plasma by far. How does oxygen get around? Red blood cells. Like 98.5% of the oxygen is dealt with through the red blood cells. So they're the backbone here. Oxygen is carried by a very particular molecule called hemoglobin. I'm sorry, not a molecule, protein. It's a protein called hemoglobin. When oxygen concentration is high, it is more likely that oxygen will bind to the hemoglobin. This is why we want to have lungs where all the oxygen is concentrated, right? We need a really high oxygen environment to encourage it to bind to the hemoglobin. When the temperature is high, binding is less likely. When the pH is low, binding is less likely. When products of metabolism are high, binding is less likely. So this is why blood helps keep us at the right temperature, right? Not too hot, not too cold, just right. Not just because that's the temperature your cells need to function, but that's also the temperature that your red blood cells need to bind to the oxygen. The temperature can't be too high, the pH cannot be too acidic, and the products of cell metabolism, like carbon dioxide and other kinds of cell poop, those rates can't be too high either. I love their picture. Oxygen in a cell, and then oxygen leaving a cell. Fantastic illustration. It really pulls the slide together. I don't think we quite would have understood the concept without that lovely illustration. All right. Gas exchange in the tissues. So now we're talking about internal respiration. Oxygen unbinds from the hemoglobin molecule. Oxygen then diffuses out of the capillary because there's more free oxygen in the vessel than there is free oxygen outside the vessel. We have just set up a gradient. Nature does not do gradients. We diffuse oxygen out, trying to equalize those levels. Meanwhile, there is another gradient going on. There's high levels of carbon dioxide in the tissues, low levels of carbon dioxide in the blood. There's another gradient. Nature doesn't do gradients, so we push CO2 into the bloodstream to equalize those. We offload oxygen, we onload carbon dioxide. Now the blood has turned from red to blue, and we send it on back to the heart. Again, old story for us, right? This is not new information. Cool. Carbon dioxide transport in the bloodstream. Carbon dioxide will dissolve in blood plasma much more readily than oxygen will. So we get more carbon dioxide carried through blood plasma than we do oxygen. About 7% compared to 1.5. About 7% of the carbon dioxide will be dissolved in the blood plasma. About 23% will bind to the hemoglobin. 70% is carried as a bicarbonate ion. Bicarbonate is like baking soda. It's two carbon atoms stuck together, bicarbonate. Okay, I feel like we've gotten through all of the anatomy stuff. Now we start to look at the pathology stuff. We understand what the system is supposed to do. You get a much keener insight into what the system is supposed to do when you watch the system fail and you see how it breaks, and when it doesn't work, you get a much better idea of what was supposed to happen. The first one we'll look at is hypoxia. The prefix hype or hypo means below. The OX is oxygen. and the suffix IA indicates a condition. So hypoxia is a below oxygen condition. What's the problem here? We're not getting enough oxygen. Ta-da, the end, roll credits, we're done. Hypoxia, inadequate oxygen delivery to the tissues. This can be caused by a lot of different things. There are many different reasons why the tissues are not getting oxygen. But if they are not getting oxygen, that is hypoxia. So we have hypoxic hypoxia. Why are we not getting oxygen? Because the blood does not have oxygen. This could be a lung issue. This could be a membrane issue, right? But the blood itself is not rich in oxygen. We have anemic hypoxia. This is a lack of red blood cells. So why are the tissues not getting oxygen? Because I have no blood or blood cells, right? So with hypoxic, I've got blood, there's no oxygen in it. With anemic hypoxia, I don't have any blood. Ischemic hypoxia, I have oxygen and it's in the blood, but this area isn't getting blood flow. Ischemic hypoxia could be something like a stroke. So a blood vessel was damaged and now a section of brain does not get oxygen. This could also happen in the muscle. So we're familiar with ischemia in the muscle, right? Massage therapists, we know about ischemia, yeah? No, yes, no. I'll make this brief. Okay, this is a typical skeletal muscle. Notice, inside the skeletal muscle, blood supply runs through the muscle, right through that muscle. So when the muscle is short and tight, like people come to massage therapists because their muscles are tight, right? When muscles shorten, they don't just get shorter, they get thicker. Think about your bicep, right? When it contracts, it gets shorter, but it also gets wider. That's why the bicep really pops. So when muscles get short, they get shorter, they get thicker, and it puts pressure on the walls of these blood vessels. So when muscles get tight, they clamp off their own blood supply. That's ischemia. That's ischemia. This is what we deal with as massage therapists. We manipulate the muscle, we massage the muscle, which causes it to loosen up, which restores blood flow to the area. So with ischemic hypoxia, we could be talking about ischemia in general, like in a muscle. We could be talking about something specific like a stroke. So there's been a blood obstruction and now a section of tissue is not getting blood flow. We also have histotoxic hypoxia. Cells are unable to use oxygen because they have been poisoned. This is how cyanide works. Cyanide blocks the cell from being able to utilize oxygen. And if they cannot make oxygen, they cannot make ATP. And if you cannot make ATP, you cannot afford to live. Your cells cannot afford to replicate or take in nutrients or actively put things across a membrane, right? Active transport across a membrane requires ATP. They cannot afford the ATP that lysosomes need to digest. We don't have ATP to synthesize new proteins. All of it, all cell function stops when we do not have ATP. And that is how cyanide will kill you. So how is breathing controlled? Well, it's controlled both in the lungs and through the nervous system. So we have autoregulation in the tissues. These are highly active tissues that receive more oxygen due to the increased release of hemoglobin. We have local chemicals called vasodilators. They increase the size of blood vessels, increasing the flow of blood. Vasodilators will build up in active tissue, causing an increased blood flow. We also have autoregulation in the lungs. The alveoli, with their higher oxygen concentration, receive higher blood flow. Bronchioles will relax when carbon dioxide levels are high. These are automatic processes. We don't have to do anything. The body just handles these things, making sure that our respiration rate, the oxygen amounts, right, tidal volume, all that stuff stays within normal parameters. The brain also has quite a bit of control over breathing. You've probably noticed in your life, you don't really control your breathing. It just kind of happens automatically. You just do it until we start doing something like meditating, or when I tell you, take a deep breath, and you guys all take a deep breath. We are able to switch to what I call manual breathing, where you are actively controlling the process. But manual breathing can also be turned off, and you just go to normal automatic breathing where you don't really think about it. The brain has nerves that connect to the respiratory muscles. So those normal nerves go into skeletal muscles. The nerve that plugs into the diaphragm, that plugs into SCM, pec minor, scalenes, normal skeletal muscle nerves. Voluntary breathing is limited. We do this through the involuntary system that gets taken over. I'm sorry, the involuntary system takes over if voluntary breathing stops. So when you stop manually breathing, brain takes over. You don't have to think about it. Involuntary breathing, which is what most of us are doing, rhythmic impulses are sent from the respiratory centers in the brain stem. Brain stem is way down here at the bottom. The impulse rate is influenced by chemicals in the blood. It's also influenced by the autonomic nervous system, emotion, and pain. So all of these kinds of stimuli change the brain's signal to tweak the rate of respiration. So when we're in a lot of pain, or when I'm experiencing intense emotions, breathing rate goes up. Other things that control breathing, we talked about chemoreceptors. Last time we talked about chemoreceptors, we were talking about the circulatory system and how arteries had chemoreceptors in them that are sniffing out pH changes, right? If the blood gets too acidic, then we up our respiration rate and get more oxygen into the system to bring the acidity level down and try to increase the pH numbers. We have these peripheral chemoreceptors in the arch of the aorta, as well as in the carotid artery, because the two main places you really want to test the blood fresh out of the heart, just before the brain. All the other organs are secondary, guys. Heart and brain, gotta have them to function. So the blood, right as it comes out of the heart, we're gonna do a quick little pH test, and then the blood heading up the carotid artery before it gets to the brain, we're gonna do one more pH test before we let that blood in the brain. There are more central chemoreceptors found in the brain stem. The brain stem is also sniffing out chemicals, directly tweaking respiration rates based on what it finds. Low oxygen, high carbon dioxide, low pH. Those factors tend to be associated with each other. Those will cause breathing rates to increase. Carbon dioxide, the presence of carbon dioxide is the most potent stimulator. The amount of carbon dioxide is closely controlled. So that's really the one that they're looking at. How much carbon dioxide is in the blood? If it's too much, the brain will increase respiration rate to get more oxygen in there. So your chemoreceptors are monitoring your oxygen levels, your carbon dioxide levels, and hydrogen ion concentration. Side note, hydrogen ion concentration, that's pH. That's the pH. Hydrogen ions are acid. So that's what we're talking about here. pH. Do you guys know what pH stands for? Potential hydrogen. So when your slide talks about hydrogen ion concentration, we're talking about pH. That's what pH is, potential hydrogen. Cool. Chemoreceptors, fun stuff. Lungs also have stretch receptors, which detect and tell the brain how inflated they are, how stretched that tissue is. They have the stretch receptors in the lungs do have an inflation reflex, which is triggered by a negative feedback system. For more information on negative feedback, see your endocrine system. The whole endocrine system is nothing but positive and negative feedback loops, just over and over and over. Super complicated system. Stretch receptors in the lungs detect how stretched the lungs are. Their purpose is to make sure the lungs don't get overstretched, because that would be really bad. If a lung exploded, it's been nice knowing you. So the inflation reflex goes like this. we start at the top. We breathe in. Tidal volume increases by about 1 liter. We add about 1 liter of air into the lungs as they expand. The airways stretch. That stretching leads to an increased respiratory rate. So once you start breathing in, you've started a chain reaction. Now you can keep breathing in more. But at a certain point, we don't have enough time. That leads, I don't even understand this. Decreased time for inspiration somehow leads to inspiration. I don't understand this. I'm going to assume it's not that important. Here is a 3-minute video. Let's learn together.
Remember to pause the recording. Remember to pause the recording if you're playing a video, right? That's something you need to do.
Yes.
Well, there you go. Seem helpful.
Thanks, Celeste. So now that we watched that very enlightening video, let's never watch that video ever again. Okay, so here's how it's going to work. Your lungs have stretch receptors in them that are detecting how stretched lungs are. When they reach their threshold, saying, bro, stop, lungs are too full, hold up. They send a signal through the vagus nerve into the pons of the brain stem. When the pons receives that signal, it inhibits your body's inhalation muscles. When muscles become inhibited, your brain stops them. So when your lungs reach a certain stretch point, the brain stops inhalation. It is a reflex arc that happens. You don't get control over it. This prevents the lungs from being overinflated. Cool. The effects of exercise. Exercise works wonders for just about every system of the body, but it's very good for your respiratory system. Breathing will increase 10 to 20 times with exercise. So remember we said normal breathing rate was like 10 to 20 breaths per minute. We're talking about 60 to 120 breaths per minute when you're exercising. This is due to increased oxygen consumption. Why are you breathing so much? Because I'm burning a lot of air, bro. Burning lots of air. This increase in lung capacity is due primarily to the increased depth of breath as opposed to increased rate of breath. Proprioceptors play a role in a change of respiration, because of course they do. Actually, before we move on to aging, effects of exercise. I feel like there was something else I wanted to say here. Ventilation increases with exercise due to increased oxygen consumption. Whatever I wanted to say, I guess I forgot it. It's gone. All right, aging. The effects of aging are also apparent on the respiratory system. Because of bone conditions like osteoporosis and calcification of the rib cage, if the ribs don't move like they're supposed to, then the chest walls become too stiff, and now the lungs they don't have enough space to expand. That caps your lung volume. If we can't drop the floor and raise the ceiling and give them space to expand, then they can't expand. So you're limited onto how much air you can take in. Over time, your body stops producing elastin, which gives you that elastic quality. So the lungs become less elastic over time. The body's decreasing production of elastin is a body-wide thing. This is why we start to get wrinkles and our skin starts to sag, because your skin also stops producing elastin, which is why it doesn't bounce back like it did in your 20s, right? It's all nice and tight in your 20s. And then as you get older, everything just starts to kind of deflate and sag. Less elastin plus the constant pull of gravity. There you go. Also, Over time, as you age, particularly when we get into older age, everything starts wearing out, including those little walls between the alveoli. So just like COPD, you start to lose surface area as you age, which also decreases lung efficiency. Chemoreceptors become less sensitive. And when they become less sensitive, we start to carry more carbon dioxide and waste products in the blood than previously was acceptable. And also your cilia start to break down. Those little hairs that keep everything moving in the same direction. Those guys age and wear out. Also respiratory infections. As you age, your immune system starts to decline. So your rate of infections starts to go up. And all those new lung infections start to cause damage to the lungs. Cilia decrease, macrophages decrease, white blood cell count drops as you age. But the good news is massage aids the respiratory system. By relaxing the body, we increase respiration rate, particularly deep breathing. Massaging the accessory muscles helps people with tension, particularly people that have difficulty breathing. Some of those accessory breathing muscles could be really tight, and relaxing those will increase the function. We can also work to release restrictions around the diaphragm and ribs. So one of the things I like to do with clients, especially just in relaxation massages, what I call raking the ribs. So you find your ribs right about here. Once you find them, let your fingers slip in between the spaces. So you're pressing in between the ribs. That's a rib right there. That's a rib right there. So what I'll do in massage, again, nice and lubricated, is you just kind of rake through those intercostal muscles. Just give them a nice little massage. And you can follow all the way around to the back. And what this does, just like every muscle, guys, every muscle gets tight, and a little bit of massage helps loosen it up. And now what we're doing is increasing the ability of the ribs to move away from each other, right? By increasing the flexibility of the intercostal muscles, we aid the ribs when we have to expand or contract them. Another really interesting one here is postural drainage. You don't really see this one a whole lot in massage particularly, but postural drainage, put this a very simple way. I have water in my cup, so I can't move it. But if I have water in my cup, how do you empty the cup? You tilt it, right? So if you're building up fluid in the lungs, how can you get fluid out of the lungs? You lay the person face up on a reclining table so that the feet are above the head, and literally posturally you drain them out. That's what postural drainage is. You literally put them on like an inversion table or something like that. And not a full inversion table, they're not upside down, but you just bring the feet above the lungs. And now the fluid will respond to the pull of gravity, and it will start to drain upwards, remember, upwards out of the lungs. Another one that is really useful, especially for respiratory therapists, is the podiment technique called cupping. Do you guys not cupping with cups? Yeah, thank you, Celeste. This one. Yeah, not cupping with cups like Chinese medicine. No, no, no. We're talking about this one. Particularly over the back, over the upper back and over the lungs. Cupping just helps break up phlegm and just break up all that congestion. Just warn your clients beforehand. When you start cupping over the lungs, afterwards, they're going to be hacking it up. They're going, it's all coming up. So just let them know you want to start carrying some tissues. Be a pal and warn them what you're going to do, because they're going to be hacking up a lung afterwards. It's good. They're getting rid of all that congestion, but you don't want them to like, oh, I'm getting this massage, and then I'm going to my wedding, and they're sitting up at the altar like, meh. That would be bad. So cupping can loosen mucus. Podiment cupping, not cup cupping. Yeah. All right, crash course. There are 2 crash course videos on the respiratory system. I highly recommend them. I highly recommend them. If you haven't watched them already, you did, Grace, aren't they awesome? I love that guy. Hank Green is like my hero. I just love that guy. He's done the anatomy stuff and they've been out for a while, but now he's doing like other science stuff. And I love him. All the videos he puts out on YouTube are awesome. He's got this new one now called like A Journey into the Microcosm, where it's like really, really good microscopes. And he just watches all these little bugs in water, like tiny little microscopic stuff in water. And it's almost like ASMR because it's like, it's very calm. His tone on those videos, he's like, look at this little flagellating lotopistrian running through. And it's so cool. Meet the Microcosmos. That's it. Meet the Microcosmos. And it's Hank Green doing his thing. And they're all just videos about like gliding bacteria and flagellating bacteria. And look at this lovely pond scum swimming around. But it's so chill. And the microscopes that they use on these videos, guys, are insane. Really, really high quality. So yeah, this guy, watch all of his videos forever. Just watch everything he does forever. But in particular, the 2 crash course respiratory system videos, can't go wrong with them. And there you have it, folks. That's our lesson for the day. Okay, so this slideshow is already on Moodle. However, there is a second slideshow on Moodle. It's a lot more text, a lot less pictures. It's not colored green, it's blue. That's just the standard PowerPoint that came with the textbook. So that one just follows along right in the textbook. It's a good one. It's a really good one. Yeah, I recommend stick with this one. What else was I gonna say? We talked about skeletal muscle. We did all that already. Yep, I believe that is about it, my friends. So we've covered all the major parts and divisions of the respiratory system. We've talked about its functioning. We've talked about the flow of blood and how the flow of blood is related to the respiratory system. We've talked about various things that can affect the respiratory system, such as exercise, aging, and massage. And we know that our right lung has one more lobe than the left. Yeah. So I think that about wraps it up for us tonight, guys. Any questions over anything we have gone over so far tonight? Sorry, I can only hear one of you at a time. All right, guys. Well, if that's it, then I will not keep you any later. If you do come up with a question, though, reach out to me. Shoot me an email or message me through Moodle, and I'll be sure to get back to you. And please don't ever think that you're bothering me with questions. I love questions. That's why I'm a teacher. So fire away. With that being said, guys, we'll go ahead and dismiss class for the night. Good to see you guys. It's a pleasure as always. I will see you all next Thursday. And before I leave tonight, I will double check the dates on Moodle. There is a quiz on Moodle that will be due before class next week. Quiz 4, I believe. Maybe it's 5. But there's a quiz. All right. Good stuff. With that being said, everybody have a wonderful evening. I will see all of you next week.